Welcome back. Day 2 of section 4.9. The antiderivative does have different names. Like if you have friends in AP Calc and they're like, oh, we're doing integrals. That's the same thing. Integrals are the same thing as antiderivatives. Integral is like more of like an operation. So it's basically the exact same thing. This is kind of like the last topic of calculus, Calc 1. Right? The last topic that we learned in Calc 1 is antiderivatives or integrals. Okay, so and I think I said this in the video. I kind of outlined. This was from last year again. I kind of outlined what like the expectation is for the rest of the semester. So really, 1, 2, 3, 4, 5, 6, 7 homeworks left to go. That's it. That's all it is out of the rest of the year. Out of your entire obligatory math classes, Beyond this, you might not. Okay, so antiderivatives. Antiderivatives. We talked about antiderivatives being, finding an antiderivative with x squared in it, right? We were like, okay, if it's an x squared, think about what the derivative would be, and then think about how would you work backward based off that. And the rule that we came up with was, and I think there was this chart as well. The rule that we came up with was, well, you add 1 to the power. Instead of kicking down the power, you kick up the power. You make the power raised by a factor of 1, and then you divide by that n plus 1 as well. And that's where we got the rule, like if I wanted to find the antiderivative of x squared, it would be x to the 3rd over 3. Derivative of x to the 10th would be x to the 11th over 11, right? It gets a little weird when we work with sine, cosines, and tangents. I'm not going to be giving you hyperbolic sines and cosines. No, thank you. The most I would ever give you is sines or cosines. Yeah, sines or cosines. That's really all I'm going to be giving you there, sines or cosines. The nice one that we will work with a lot is, since the derivative of e to the x was e to the x, the antiderivative of e to the x is also e to the x, which is kind of cool. The antiderivative of 1 over x is ln of x, the absolute value of ln of x. Yeah. Why is this the way it is? Why is the antiderivative of b to the x over ln b? Because you got to think back, that relates directly to the derivative of b to the x. If I have the derivative of b to the x, like 2 to the x, it's 2 to the x ln 2. So it's that same exponent and then multiplied by the ln of 2. So that's why you need to take that exponent, same thing, and then divide by. Instead of multiplying by, we would divide by. We take the we take the inverse. Okay. And we worked with problems like this, and then we didn't do this, right? Okay. Let me get rid of that. So this is where we'll start for today. We've got to do example 5. And we got some rectilinear motion. All right. So the first thing I'm told here is that the graph of the function f is given. Make a rough sketch of the graph of the antiderivative. Make a rough sketch of the graph of the antiderivative given that f of 0 is 2. You know what I'm going to do? I'm not going to try to put it on the exact same graph. I'm going to create a new one. Pretty much an exact copy. So we got 0, we got up to 5. 0, 1, 2, 3, 4, 5. Okay, so if that's the function, let's make a sketch of the antiderivative. Let's make a sketch of the antiderivative. Now, we've kind of already done this. We did this back in section 4.6. When we looked at using technology, okay, what was the function and what was its derivative and how does that relate? You kind of did that on a test question where I gave you the graph of the derivative and said, tell me about the original, right? Work backward. Oh, that's the antiderivative, right? Work backward, okay? All right. What do these points tell me? What are those points on the graph of the original? Like, what's happening at 1 and 3 of the original? Maximums and minimums. Maximums and minimums, right? There is an extreme value at 1 and an extreme value at 3, right? Think of this as like, okay, so this is the derivative. Let's graph the original, right? What are the zeros of the derivative? That's the maximum or minimum of the original, right? Now, is 1 a maximum or minimum? Is 1 a maximum or minimum? Well, think about it this way. It's going from negative to positive, right? So this is telling me this function is decreasing on the interval 0 to 1, and it is increasing on the interval 1 to 3. So if this goes from decreasing to increasing, what does that tell me about 1? It's a minimum point. All right, so let's make a minimum point. Now we're told that f of 0 is 2. So let's call this 1, 2. Okay, and we know that there's a bottoming out point happening at 1. Let's go right here. And then what's happening at 3? Is it a minimum or maximum? A maximum, because it is going from increasing because it is the x-axis above the x-axis to decreasing because it's below the x-axis, right? So it's increasing to decreasing. Now, I should have been a little bit more specific here. What's happening at 2? That is an inflection point, right? There is an inflection point there, and I should have been a little bit more, I should have telegraphed that a little bit more, right? So it's going concave upward to concave downward at that moment. What's happening at 4? Another inflection point, right? Another inflection point. Right? Another inflection point at 4. Let's leave it at the same spot. Now, is it going to have another extreme value past 4? No, because it's not going to cross the x-axis again on the original, right? It's not going to cross the x-axis here. So therefore, I need to say, well, it's still below the x-axis, so it's still going to be decreasing, right? It's still going to be decreasing. But the fact that this is going upward on this function tells me what? Isn't that concave up? If this is the derivative, isn't that concave up, right? Still. So I'm just going to continue making this concave up. Rough sketch. Could I make those extreme values happen anywhere I wanted them? Yeah. Those inflection points happening anywhere I wanted them. Yeah. Because I don't necessarily know for sure where it's happening there. Right? Not told the function. You know, the expectation is I could have made you do that on the on your test. Right? I guess that would have been that's a difficult problem to do. But did we have enough information to do that? Yeah. Did we have enough knowledge of that? We should have. Yes. But here's what's different between what we were doing before in chapter 4 and what's different now. Now we are saying, okay, this is the graph of f of x, which means that this is the graph of not a derivative. This is the graph of an original. We have to shift our mindset a little bit and say, this is not a derivative, this is original. So if this is original, then we would call this, they use the notation capital F, but that is the antiderivative. That is the antiderivative. If that's f of x, that would be the antiderivative, f, capital F of x. Okay? So same rules apply between functions and its derivative, right? So basically what I'm saying here is if you have capital F, if you take the derivative of capital F, what do you get? Lowercase f, right? if you take the derivative of an antiderivative, you get back the original function. It's like an inverse, right? If you take the derivative of an antiderivative, you get back the original. Okay. All right, another key concept that we have to learn about is what's called rectilinear motion. Rectilinear motion. Antidifferentiation is particularly useful in analyzing the motion of an object in a straight line, and that's where it gets its name. Straight line motion. Rectilinear motion. See the root word in there, linear? Straight line path. Recall that if the object has position function s is equal to f of t, then the velocity function is equal to v of t. Velocity function v of t is equal to s prime of t, right? Remember, the velocity is the derivative of position, right? If s of t is position, then the derivative of position is velocity. What is the derivative of velocity? Acceleration, right? This means that the position function, now, shift our mindset now, right? That's something that we knew from past. Derivative of position is velocity, derivative of velocity is position. So now what I can do here is work backward and shift our mindset and say, well, what if I started with the acceleration? How would I find velocity? Take the antiderivative. How would I find position if I know velocity? Take the antiderivative of velocity. Right? Likewise, the acceleration function a of t is equal to v prime of t, or s double prime of t. So the velocity function is an antiderivative of acceleration. Right? If I have the acceleration, I can work backwards to find the velocity just by taking the antiderivative. And the nice thing about rectilinear motion is it's usually polynomial. Usually polynomial. And polynomial functions are super easy to find the both the derivative and the antiderivative for. Right? Okay. A particle moves in a straight line and has acceleration given by the function a of t is equal to 6t plus 4. Its initial velocity is v of 0 is equal to negative 6 centimeters per second. And its initial displacement, s of 0, is equal to 9 centimeters. Find its position function, s of t. So I can somehow measure this particle's acceleration. Somehow. Okay? I can somehow measure the acceleration. And I can evaluate that the acceleration, what type of function is the acceleration? What type of function is that? That's a linear function, right? That must be super easy to find if it's linear, right? If I have 2 points, I know the acceleration at one point, I know the acceleration at another point. Can I just use slope-intercept form to find, or point-slope form to find that equation? Super easy to find the acceleration function. I see the acceleration function is 6t plus 4. I know that I started this particle out with a velocity of negative 6 centimeters per second. So moving in the negative direction, straight line path, right? Straight line path. I'm not varying. It's just straight line path, not moving 3 dimensions or anything like that. Just straight line path. Its initial velocity is negative 6 centimeters per second, and its initial displacement. So how far away were we from start? How far away from start were we? 9 centimeters. So its initial position displacement is 9 centimeters away from 0. I know that I've started this off, so we're at positive 9. I've started this off moving it backward at negative 6 centimeters per second. And I know that the acceleration is 6t plus 4. So this must be super easy to find, that the original displacement is 9 centimeters. And I had to have given this some effort. I had to given this some initial velocity of negative 6 centimeters per second. Let's figure out all those functions. Let's figure out the velocity and then the position as well. Okay, so remember the velocity, v of t, is equal to the antiderivative of the acceleration. All right, so if it's the antiderivative of acceleration, we kick it up, divide by the power, put a t on there. What do I have to tack on at the end? Plus c. Reduce that. V of t is equal to 3t squared plus 4t. Well, what is c in this case? What is starting velocity? Isn't our y-intercept the starting value, right? What is our starting velocity? Negative 6. Negative 6. What if I had given you like v of 1 is something? You know, what if I had given you a value? Could I still run that value? Of course. Just plug in 1 in for t, set it equal to whatever the value would be, right? And then solve. All right, now its initial displacement. Well, we know that s of t is the antiderivative of v of t. Well, kick it up, divide by the power. Kick it up, divide by the power. Tack on the t. Let's call it a d. Let's reduce it down. So that means my position, t to the third plus 2t squared minus 6t plus what? Plus 9. It only asked for position, but we needed to get through velocity, right? There's no way to go from acceleration to position without going through velocity. So just by knowing that the acceleration was 6t plus 4, I can get that the position is some weird, wacky cubic function, right? By knowing what the acceleration was, that linear acceleration, starting velocity, starting position.
Attention, please. Ninth graders, last name starting with A through M. Please go to the main gym now for spring pictures. That's ninth graders, last name starting with A through M. Please go to the main gym now for spring picture day. Thanks.
Okay. Projectile motion. Projectile motion instead of rectilinear motion. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, which is 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height, and when does the ball hit the ground? All right. Here's the first thing that I need to know. Okay, what is my acceleration function? Am I told the acceleration function? What is that 48? What is 48? What's that? The starting velocity. Right? Right? Starting velocity. What's 432? Starting position. What am I asking for when I say find its height above the ground t seconds later? That's position, right? Find its position. Find its height. So this is going to say, okay, so what is s of t? Well, if I want to know s of t, I got to know velocity to do the antiderivative. And if I got to know velocity, I got to know acceleration to do the antiderivative. So what is does this tell me any more information? So what is the acceleration? Gravity, right? What is the acceleration acting on all things on Earth? Gravity, right? Now, I bet the number that sticks out in your head is 9.8, right? 9.8. But what is 9.8? What's the terms? Like what terms are that? 9.8 meters per second. This is in feet per second. So we got to actually turn that into acceleration negative 32 feet per second. I know. This calc book uses a lot of feet. Okay. Negative 32. That's the acceleration due to gravity in feet per second. Feet per second squared, sorry. Acceleration is unit per time squared. Okay, so that's the acceleration, right? That's the acceleration. Does it matter how much time? This is interesting. Does it matter how much time something is in the air? Does that change the acceleration due to gravity? No, right? The acceleration due to gravity is always constant. So is there actually a t value in there? No. There's no time part of this. What comes with it is the when does time play a role? Velocity. Right? Velocity. So find the antiderivative. Okay. Negative 32t, I would say plus c, but I know, what is that? Plus 48. And then I can keep going and say, well, s of t is equal to negative 32t, oops, forgot my 2, 32t squared plus 48t, we'll say plus d. I know what, actually, you know what? Why say plus d? What is d? 432. Oh, I forgot to divide by 2. Forgot my divide by 2 did. And then, so therefore, position is s of t is equal to negative 16t squared plus 48t plus 432. So there's position. That's the answer to my first question. Give me an equation that I could find the height at any given moment. Okay, s of t. You tell me 5 seconds, there you go. Plug 5 in. Okay, when does this ball reach its maximum height? Now, there's a couple different ways to do this. You know what's interesting? I used, back when I made this key, I used negative b over 2a to find the maximum point, because that's the midline of a parabola, right? But I didn't actually need that. How do you find the maximum point? Well, you take the derivative and you set it equal to 0, right? What is the derivative of position? Velocity. Set velocity equal to 0. Negative 32t plus 48 equals 0. So t is going to be equal to, got negative 48 divided by negative 32, which is 1.5. So after 1.5 seconds, the velocity is 0, which means that's at its maximum height. Why do you say numbers? Interesting. And then I say, well, when does the ball hit the ground again? When does the ball hit the ground again? I think I'm stuck here. I think I have to do, do I have to do quadratic? I think I have to do quadratic formula. The opposite of b plus or minus the square root of b squared minus 4ac all divided by 2a, negative 32. All right. So when does the ball hit the ground? Let's see what the discriminant. 48 squared minus 4 times negative 16 times 432. Oh, that looks weird, but that's okay. It'll work. I square root that, and I get 173.07. 173.07. So negative 48 plus or minus 173.07, all divided by negative 32. Okay, so let's run those values. I want to throw out the negative one, right? So I got to do the minus.
Starting with N through D, please go to the main gym for spring pictures now. That's ninth graders' last name starting with N through D. Please go to the main gym and have your spring pictures taken. Thank you.
When is the ball going to hit the ground again? 6.91 seconds. I could run the other value. I could run the plus, but it's just going to get me a negative number. Okay, that ends the formal notes for section 4.9. But I do want to go on this little tangent here. No pun intended. I do want to go on this little tangent here. You know, back in algebra 2, I'll think back, the good old days. of algebra 2. I taught you this function, negative 16t squared plus v sub o t plus h sub 0, right? That's how we learned projectile motion way back when we didn't know better, right? That was our equation of projectile motion. What was this? Initial velocity. What was this? Initial height, right? And this was all calculated on feet, right? If this was meters per second, that would be a negative. Actually, no, that would be a negative 4.9. But we'll talk about that in a second. This all stems from antiderivatives. What is the acceleration due to gravity? Negative 32 feet per second squared. So that would be my initial velocity, or sorry, excuse me, the velocity function would be negative 32t plus, and then we would say plus c. But that c, isn't that our initial velocity? Isn't c our initial velocity? Oh, shoot, sorry. Right? That's our initial velocity, which is, in other words, v sub o, v sub 0. Well, position, okay, keep going with the antiderivatives. Oops, sorry. Negative 32. Oh, what the heck did I do? Flip my t and my 2. T squared over 2 plus v naught t plus, and then I would say plus d, but we know d is our initial height, right? H naught. Okay, just simplifying that down. Do you see the connection now? That's where that equation comes from. Right? This could all be calculated in meters per second as well. Like that number that sticks out in your head, that acceleration due to gravity is negative 9.8 meters per second squared, right? Run that same calculation. That means my velocity function would be negative 9.8 times t plus initial velocity, right? So position would be negative 9.8 t squared over 2 plus v naught t plus h naught. Negative 9.8 divided by 2. And I don't know about you guys, when I was in physics, like we always had this equation sheet, and this was always on the equation sheet. Like there was an equation sheet that we always used, and that was a position function that we used all the time. And I always thought, where did that negative 4.9 come from? Like, why not? Why did it change from 9.8 to 4.9? But I didn't know then. It was about the antiderivative, right? It was about the antiderivative cutting it in half. That's what it was doing there. All right, sorry, I'm done. I just thought I think that's so cool because like you learn it in physics. Do you guys learn this equation in physics? Ever use that one? Oh, really? We had to memorize that one. That's true.